Reinforcement learning is rapidly becoming the secret sauce behind cutting-edge AI agents. For example, OpenAI Deep Research Agent was explicitly trained with RL. As OpenAI note, it was trained on real-world tasks requiring browser and Python tool use using the same reinforcement learning techniques behind OpenAI O1.
The model that powers Deep Research is a fine-tuned version of O3, which is our most advanced reasoning model. And we specifically trained it on hard browsing tasks that we collected, as well as other reasoning tasks. And so it also has access to a browser tool and Python tool. So through training end to end on those tasks, it learned strategies to solve them. The resulting model is good at online search and analysis.
Anthropic, Claude, and other modern agents similarly leverage RL to specialize in coding and reasoning tasks. This trend of doing post-training on LLMs with reinforcement learning using verifiable rewards, also called RLVR, is gaining a lot of attention in 2025. Unlike other RL paradigm in the past like RLHF, the rewards in RLVR are objective and verifiable, meaning the environment can automatically verify outcome without human intervention. So the key component of RLVR are the following. We have first the dataset over here, which is usually a set of prompt question like synthetic QA pairs. We have the policy here, or we'll also call the actor, which is the LM that is going to generate the response, often via like chain of thought. So in this framework, the LM is kind of the agent, so the policy, and given a prompt, it will generate a chain of thought that correspond to the action, or also we call it the rollout. In this setup, the action can also be tool call, which will be creating some async element to them, where the text will be then aggregated. With these actions, then we have the reward or the advantage. It's basically a score computed by the environment for each of the rollout, and these are verifiable. So for example, it's +1 if a math answer is correct or 0 otherwise. Finally, with all these rewards, we have a policy update algorithm that we'll take a look at them, and something like group relative policy optimization, or also DAPO can also be used to refine the model based on the rewards. All these elements, the data, tools, reward function, policy update, together define an RLVR environment and are the subject of today's video. So we're going to take a look at the performance of RLVR on small models, the core idea being RLVR versus RLHF, some open source library to build an environment. We'll also take a look at a few environments made by the community. And finally, we'll chat with Will Brown, the maintainer of Verifier, and RLVR environment library to see what's next. For those that don't know me, I'm Yassine, a published researcher and machine learning practitioner who love to teach. Do consider subscribing to the channel to learn technical topics related to machine learning. Until recently, RLVR environments were kind of scattered and fragmented. There was no established platform for exploring and sharing train-ready RL environments. This fragmentation is kind of risky because big labs are building like proprietary environment for closed model, so open source model might fall behind without a shared ecosystem. So this is where today's sponsors come into play. Prime Intellect with their Environment Hub. The Environment Hub is a community-driven platform for publishing, versioning, and sharing RL environment. Like Hugging Face for model, the Environment Hub lets researchers push new environment packages and track version. Under the hood, it all uses the same verifier framework, which defines how to specify an environment. This common schema allows environment to plug into standard tools for evaluation and training. It also handles agentic tool using tasks out of the box. In summary, Prime Intellect provides the full stack, so the environment and the infrastructure, so you can focus on task design versus wrangling the code. You can check out the Environment Hub over here to discover, use, and create RL environment. So, we already got an intuition that RL for fine-tuning is actually useful for massive model like O3 for doing specific tasks like deep research, but we'll see that it's actually useful across all model size. In practice, purpose-built RL-tuned model can outperform general LM on a very narrow specific task while using less compute and producing faster answers. Basically, you're trading generalizable ability of LLMs for narrow performance. So let's use a case of OpenPipe Art-E, an email search agent, which was built with RLVR. The team generated a synthetic email QA dataset from the Enron corpus and trained a small model via gRPO.
So this is what it looks like when everything goes right. And you can see it actually starts out significantly worse than these other models from the start. That's because we started from a Qwen 2.5, the 14 billion parameter one. It's a relatively small model, relatively weak model, and so it was doing much worse than these initially. So for this email agentic harness that we had, we benchmarked the cost on O3, O4 Mini, and our model. So if you wanted to do like 1,000 searches using O3, that's going to cost $55. which is a lot. I think for most use cases that probably would be cost prohibitive just from a unit economics point of view. On O4 Mini, we're down to $8, but that's still quite expensive. And then we drop another order of magnitude by moving to this smaller Qwen 2.5 14B. On this task, we were able to get significantly better latency. This training run, it cost us about $80 in GPU time. It did take about a week of engineering time to build this, and caveat that was with an engineer who is familiar with this domain and had quite a lot of experience with machine learning and RL.
So once you have a workflow that makes sense, going the RLVR route gives you higher performance on each task, lower latency and total cost, and new creative solution with less human bias. On that last point, there is something quite fundamental in designing properly the model learning environment and just letting it learn. As seen with NVIDIA Pro RL training run on a 1.5B model, you not only improve the score, it also, like the authors say, show reduced n-gram overlap with pre-training data. In other words, the fine-tuned model found novel reasoning paths and solutions that were unlikely given its original training data. So let's take a look at the core difference between RLVR and RLHF, which as you'll see are pretty obvious. So RLVR for LLM is conceptually similar to RLHF. It's kind of like the same framework. The difference is that the reward is objective and verifiable. If we look on the left here, in RLHF, we have this thing called a reward model, which is trained on human judgment to assign a specific score. So this is usually expensive. You have to get a heck load of data and then you have to annotate them and stuff. In RLVR, we define a specific check. So here, if it's correct, we get this. Otherwise, we have a 0 or -1 or whatever it is. So basically, the policy will generate a bunch of rollouts, and then it will go through this verifier that will be able to check if it's good or not, right? And usually there's some parser element to it, be able to bring it to a format that the verifier that is a bit more deterministic can take a look at. This also, by the way, could be a LLM. You can have a LLM as a judge type of verifier. So the RLVR will kind of not need any of this preference data. It will not need this reward model, but what you will need is to be put into an environment. So have the proper setup around it in order to be able to, given a rollout, give a reward that is objective and verifiable. The algorithm of choice usually in RLVR is GRPO. And back in the days over here, it was PPO for this other one. So the main advantage here for RLVR versus RLHF is that it's more scalable, it's cheaper than RLHF to run because there's no large reward model or critique that is needed. Although very nascent, this paradigm has enough benefit for the open source community to pitch in their effort and create tools to do the heavy lifting. Notable libraries include ReasoningGym, OpenPipeArt, so agent reinforcement trainer. We have the Hugging Face TRL, and we have the verifier from Prime Intellect Core Framework. The verifier framework built by Will Brown is what powers the environment hub we're going to explore in a few, and is built in a way to be as composable as possible by following a few steps. So each environment module exposes a load environment, which return a ready-to-run environment object. With this approach, researchers have already created interesting tasks like Math with Python Toolkit, logic puzzles, and vision reasoning problem. If we dive deeper into the verifier specs, it has roughly these 7 steps. For these 7 steps, we're going to actually use the Math Python environment from Will Brown, just to kind of illustrate everything. So the first thing you have to do is actually define a dataset to give to the environment. If we dive a bit into the mathpython.py, you see that we're going to use load example dataset, and then we're going to actually give it our dataset name, which is going to be math over here. If we dig a bit into the util, actually math is this specific dataset, which is competition math in this specific repo. Usually this dataset is a Hugging Face based dataset, and each entry needs at least like 1 prompt or question. And optionally, you can also include like an answer column if you want like ground truth for scoring. There's also like the info column if you need auxiliary metadata. It will then give this data set to the model during training and also during the evaluation stage. So the second step here is to choose an interaction style that you want. So if your task is like a simple kind of QA type of stuff, you can use the single turn environment class where the model will just give 1 response and like you're done. If it's a multi-step setting where the environment reacts and the model has to continue or not, you have to subclass multi-turn env. If you want to let the model call tool or run code, you have to use a special class like toolenv, stateful toolenv, or pythonenv. In this case, it's pythonenv. Yeah, I saw it here, over there. Then the third step is like you have to actually implement the environment logic. In this specific environment, it's kind of easy because the LLM just need to call whatever tools you need in Python. So the environment logic is encompassed with the system prompt over here, which says use Python for all calculation, give your answer inside box over here, and the fact that we have the proper parser. We don't need to do anything fancy over here. So step 4 is you have to define a reward function, and reward here are provided through what we call rubrics. So a rubric is just like a function that takes the prompt, the model completion, and some extra info if needed, and output a score. It's like a collection of one or more reward function. So each reward function in this rubric is like kind of like a scorecard where it inspects the final output and sometimes the intermediate state and whatnot and return a score, but each of them will return a score that will be aggregated. One function might check like for correctness, another might check for formatting, and then all of these are kind of combined into a single reward. In this case, we're using a few different reward functions. We have first here the math rubric that is passed into this environment, and this environment will also produce a bunch of stuff which we're going to be using, and it's going to be the environment rubric that we're going to have here. And then also we're using a tool rubric, and then this is what we're going to also use. So these two will be kind of grouped together into our current rubric here, which will be the final reward function. So the math rubric kind of look like this, where we're going to check for the correct answer, right? So we're going to have the reward function for that. There's also like this tool rubric that we're using, which will kind of count the tool call in the completion message. And then we're going to aggregate it all together with the rubric group. Step 5 is to add a parser, right? So if the model output has a required format like XML or JSON, you can define a specific parser to extract structured data or check some formatting. In our case over here, we have the parser over there, which will extract boxed answer, which kind of look like this. So we told it to put the stuff into a box, and then we're going to extract it from the box. The 6th step is to package the whole thing into an environment. So all these pieces that we saw are kind of brought together into a Python package. That way the dependencies are kind of isolated, and your model will expose the load environment function that we just saw. So this one here, and then this will return the instance of the environment to the environment hub. And once you're done, you can run the evaluation or training with the CLI. So here you can use UV run VF eval and then just run math Python, because that's the name of this environment package. For training, the library can provide gRPO trainer. So it's an implementation of gRPO. It's kind of built in to plug directly with the prime RL system, but you can actually use it anywhere by setting it up like this. There's a whole variety of environment in the hub you can find, like these 3 that were submitted to me by my community. So we have MLE Bench by Crete, which is an environment that provides a standardized benchmark to use machine learning model to create machine learning model. So training, evaluation, comparing architecture, and hyperparameter, all that stuff. We then have this one, if eval confusable by Oso, which is kind of an adversarial type of setting where the environment is designed to test model robustness or error behavior on very confusable elements. So adversarial example, near duplicate input with like subtle perturbations. We also have this one, the multi-agent path planning environment by Salty Duck. So in this one, it's kind of a simulation scenario with multiple agents moving in an environment where we need to plan trajectory while avoiding collision, kind of optimizing routes. The jump between using an already built environment and creating one from scratch might look a bit daunting. So this is why I'm joined by my friend Alexine, who contributed an environment to the hub recently. She will walk us through her environment implementation, which is inspired by the paper Vision SR1, Self-Rewarding Vision Language Model via Reasoning Decomposition. In Vision SR1, the model first generates a self-contained visual description of an image, then uses this description to answer a question. The reward is given for both the accuracy of the description and the final answer as a self-reward that reinforce visual reasoning.
Hi, I'm Alexine. I recently worked on some environments for Prime Intellect. Let me show you one of them. Vision SR1, a self-rewarded VLM environment that teaches models to actually see before they think. So let's check the paper quickly. So the idea behind Vision SR1 is quite simple. Most vision language models don't really look at the image. They just guess from text priors. They see a few words like dog or snow and complete the sentence statistically. The authors wanted a setup that forces the model to ground its reasoning in what it actually perceives. So Vision SR1 splits the task into 2 passes. As you can see here, the first pass is see, think, and answer. The model gets the image in question and must first write a detailed description inside the description tags. Then it reasons step by step and finally give the answer in boxed. The second pass removes the image completely. The model only sees its own generated description plus the question and must answer again. If the description was good enough to recover the right answer, it gets a self-reward. This two-stage design lets us test whether the model's visual understanding was real or if it was just lucky with language. Let's look at how the environment actually works. As we can see here in our Vision SR1 folder, we can find the same files, the PyProject, the README, and the Python files for the environment. In verifiers, an environment is basically an MDP, and we can think of it as three components: the dataset, the RNS, and the grader. The dataset gives us the problem and the ground truth answers, when the RNS defines how we present those problems to the model. For example, the prompt structure or what messages it sees. And then the grader defines how we evaluate the model's output and compute the reward. As I mentioned before, Vision SR1 used two paces and therefore two different environments. As you can see here, there is two Python files for our project because in a multi-environment reinforcement learning pipeline, the image would otherwise stay attached during every rollout. That makes it impossible to tell if the model actually understood the image or if it's just copying patterns from pixels. So we split it. Pass 1 still has the image. It forces the model to see, think, and answer. Pass 2 removes the image. It refeeds the model's own description to see if that perception was enough to recover the right answer. So let's have a look at our first pass. As we can see here, the dataset just here is Vision SR1 47K on Hugging Face, and it contains image, question, answer triples. Then we have the RNS, which is just over here. And the RNS is built in the function prompt. So it attaches the image converted to a base 64 data array and enforces the specific output structure. So we have the tag description for visual perception, then the think tag for reasoning, and boxed for the final answer. That format is not cosmetic, it's how we parse and grade later. We can find also the prompt for pass 1 from Vision SR1. Will interact with our model. And then we have the grader. It lives in the rubric section just here, and we define two reward functions. The first one will be pass 1 accuracy, which checks if the boxed answers matches the ground truth, and pass 1 format, which checks that the model respected the full description things boxed layout. The final result is this formula just here. It means that we mostly reward correctness, but we still give a small bonus for keeping the structure clean. Then let's check our second pass. So now the second environment builds directly on top of the first one. As we can see here, in this function, the dataset isn't images anymore. It's the save results from pass 1, reinferenced through this HFIG arguments, and each record contains the questions, the model's description tag, text, and the original answer. For the RNS, we have pass 2 templates, so the model must reason again without seeing the image. For the grader, now it's quite different because we actually use 4 different signals. Just here, so we will have the visual, which is the correctness of the new answer. So basically this is the self-reward. And we will find again the pass 1 accuracy and pass 1 format from the previous environment, and finally the description format. We can see here that there is the total reward with the same weight. So if your description from pass 1 was useful, pass 2 confirms it by giving you that extra R visual bonus just here.
Thank you very much, Alexine, for the walkthrough. Check out her environment, folks, and go follow her on Twitter. Now, to tie up this tutorial, I'm joined by the one and only Prime Will Brown, who will be able to talk to us about the Verifier library in more details. So Will, thank you for coming.
Hey, how's it going? I'm Will Brown from Prime Intellect. Great to be here, and thanks for having me on.
So I have 3 questions for you. The first one, what did the development of Verifier look like from like the early conceptual ideas that you had, like I think in January, to like what it is right now? Like what was the flow looking like?
Yeah, great question. So on one hand, there's a lot of stuff that's changed, but I'm also happy at how little has changed in terms of the end user experience. So there's a lot of stuff that we've had to do to kind of like make it more flexible under the hood, more adaptable to different trainers, and support kind of different integrations. But a lot of the user-facing API, like the way you define an environment and the notion of a rubric and the interaction protocol, a lot of this is essentially exactly the same as it was when it started. And so like I think there was a lot of kind of time that I spent thinking at the beginning of like, okay, what should the interface be? What's the kind of the right building blocks? And I think getting those to a point where they were really flexible, I think we've been able to kind of not have to change too much to be able to do the stuff we want to do. In terms of like what you can do with it, though, we've been growing this quite a bit. The work I've been doing at Prime Intellect, and the Environments Hub. And so like on one hand, the Environments Hub, as you've talked about, is like the goal is to have it be something where it's really an environment SDK. And so I think initially we had these like pieces separated as like trainer classes and environment classes. But I think the biggest kind of structural change is that we've really delineated this way of having an environment be a standalone package that imports verifiers. And then that verifiers can then be a spec that is very usable by other trainers. So it's not just the trainer that's included with it. We use it in PrimeRL. SkyRL supports it. There's a number of other ones that we're kind of working on as well that I'm really excited about to share soon. But I think the goal with it really that's come into being is that we want it to be a toolkit for people to use to go make environments rather than itself being a collection of environments. Right. The Environments Hub is where we want the collection to be and where people can then like pull and push and like use environments and discover and contribute environments. And we also want it to be like really flexible for other trainers to adopt. So it's not intended to be like a one size fits all thing. It's intended to be a layer that is like both like in some sense it's like fairly unopinionated. I think like one of the kind of design criteria I've had for it is like if an eval is like a popular eval that people care about, it should be very easy to port into verifiers. And so that's been doable so far where like pretty much every eval that we've looked at, like it's pretty straightforward to kind of just like move the pieces into place. And so I think that is kind of like one of the overarching design criteria. In terms of like where we're headed next, I'm super excited about, there's a couple things that have been like simmering for a while that it hasn't yet been time to do because other things were kind of more urgent first, but multimodal is coming soon. Okay, wow. And kind of more complex agentic rollouts with branching and kind of sub-agents is also very much on the near-term roadmap. And so those are kind of the most exciting things in addition to some other really cool trainer integrations in the works.
Okay, cool. This is very interesting. And like in terms of the environment hub, I understand all these other environments you want to add to this, but like how far are you guys willing to push that part? What's the kind of long-term vision here?
I mean, I think the long-term vision is just the world is going to need to make a lot of RL environments. We think that making RL environments is going to be like a very standard piece of like essentially software life cycles. And you need an ecosystem around that. I think like any good like open source project that becomes like load bearing in a sense where people are actually building on top of it is going to grow in so many different directions. And so our goal is to have it be a foundation that can foster this growth in lots of different directions. And we're excited to kind of see where that all goes. But I think like we want it to be really easy for people to do RL fine tuning. We want it to be really easy for people to think about RL environments and understand how to take their existing applications and transform them into environments so that they can train in them and have their actual products be things that are amenable to models that have been fine tuned with RL.
Cool. And I think this ties up perfectly with like the clip that I showed previously about like I think it was in a talk that you also was there presenting from OpenPipe, and they showed like their performance latency cost trade-off, but like for $80 worth of GPU, like you can get a piece of your workflow with RL that is better than like the big LLMs and cost way less and like have less latency and all this. Like to me, like it really looked like a free lunch, right? I'm very aware about that. But like, what do you think will be the role of like RL VR in the in business application for LM? Like where in this workflow will go, and like how big of a piece you think it will play?
I think so. I think small models are awesome for research. I do kind of think that like real world complex applications, if the goal is to be a stand-in for frontier models, you will want to go to much larger models that are a little bit better natively at going out of distribution. But I think the way you can do this, I think you actually can still do this very efficiently in about that same cost regime with LoRa fine tuning and efficient serving of large mixture of experts models, which is kind of where we're also pushing. So we're kind of PrimeRL is like our industrial grade trainer stack, which we've been scaling this to like 100B plus mixture of experts models, which are still like 10 to 20B active. And so this kind of means you get the kind of training efficiency and inference efficiency of small models with the kind of native knowledge and reasoning capacity of much larger models. And so like in that sense, it is kind of a free lunch. And so I see kind of that being the way you can like for example, like I think there's a lot of people who actually do use DeepSeek in prod. Maybe DeepSeek isn't quite as good as GPT-5 or quite as good as Claude Sonnet 4.5. But if you could take DeepSeek and you can cheaply RL it on your task, I think that is really like the winning use case for a lot of people. And I think that's kind of where the ecosystem is likely headed.
Cool. Well, thank you, Will, for coming to this tutorial. Really, really useful. I have plenty of other questions, but I think that's gonna be it for this tutorial. Thanks, Will.
Thanks so much.
And that's it for today, folks. I hope this was useful, and I wish you all a great rest of the week.